Pavlick. In fact, if you're curious of the course of evolution of the findings and the ideas of Ellie, there's also a video of her talk during the seminar. You might want to have a look at that. I'll be curious to see where we got from there. Ellie Pavlick is an assistant professor of computer science at Brown. She received her PhD from Penn in 2017, where her focus was on paraphrasing and lexical semantics, the right topic. Ellie's research is on cognitively inspired approaches to language acquisition, focusing on grounded language learning and on the emergence of structure or lack of structure in neural language models. Ellie leads the Language Understanding Representation Lab called LUNAR, which collaborates with Brown's Robotics and Visual Computing Labs and with the Department of Cognitive Linguistic and Psychological Sciences at Brown. And with that, it all is in the hands of Ellie.
Thank you so much. Yeah, there's pretty good amount of overlap with the talk I gave at the seminar. So hopefully not too redundant, but I think there's some difference in the arguments, and we have some new results as well. So I blame it on the new baby in the fall that avoided a total overhaul of new results. Great. So I wanted to talk about this question that I think was a pretty big theme kind of throughout this summer school of kind of what language models or their success tells us in terms of theories of language or understanding more generally. And personally, I'm kind of taking this position that they're not theories of language understanding yet, but I think there's a lot of work that's being done that hopefully this is changing in a fairly reasonable time frame. So I want to thank students and collaborators whose work I'm talking about today. So I won't spend much time just saying we all accept that language models are good at a lot of things in language. But there's this question of whether they're like what we would call a theory of language, whether the language models themselves should change anything that we think or change any of our beliefs about language. And here I'm using kind of language and LLMs as maybe shorthand for AI and intelligence and cognition, and that's probably an overuse of the words, but I kind of use these things interchangeably because I'm focusing on language and LLMs. And the problem that comes up when we think about this question is basically this, that we have what the language model is to us is this kind of cartoon picture of a ton of nodes that are just sitting there. They're nondescript, undifferentiated, just a giant mass of associations, and they're getting language as input in the form of text and internet and maybe speech. They churn for a little bit and they produce some text as output. And since this thing is what we generally call a black box, we don't know what's going on inside. It really doesn't feel like it is useful at all as a theory, because I think Ronnie Katzer spent a lot of time in his talk talking about the point of a theory is explanation. Like the reason we're engaging in linguistics and cognitive science or any of these other fields is to get an understanding of kind of an intuitive understanding and a predictive explanatory understanding of how something like language or cognition works. And if we don't understand how the language model works, I guess it's kind of a who cares, right? Like it's like, this is an interesting tool, but it doesn't help us understand language. And so I really liked in Ronnie's talk, he talked about this idea of the explainability assumption, and he was talking about it from the perspective of thinking about humans. And what he was saying was that basically, humans and our language and our minds and our brains, these are complicated things. They're extremely complicated systems. But we just assume as a starting point that they can be understood, that they are explainable. And that's the whole kind of scientific endeavor, is we're going to grant that there is some simple model that we can, intellectualize as humans that will allow us to understand how language works or how the brain works or how the mind works. And if we're wrong, then maybe we're wasting our time. But, if we don't make that assumption, then we're not even going to bother and we're going to learn nothing, right? And in general, that's borne out in practice. We've learned a lot by assuming that these complicated things can be explained in simpler terms. But then there's this kind of asymmetry, and I was even there in Ronnie's talk where we don't grant this the same assumption for LLMs. So it's very common that people just dismiss LLMs out of hand as candidates for providing theories and insights in some non-trivial way because they're complicated, and so they're black boxes, right? Or as Gary said, they're kind of just next word prediction. And so the kind of approach I want to take, I want to advocate for is that we should, as a starting point, we need to approach the study of language models with this same kind of charity and curiosity and grant this same explainability assumption as we do for humans. And I think if we're doing this and if we can understand how they work, it's very likely, I personally think it's impossible that we would be able to do this and not generate some insight of value to understanding humans and language more generally. But of course, that's something we can talk about more in the discussion. But this is a very long game, right? Understanding large language models or these complicated AI systems, it might be a many, many, many year endeavor. I think it's one worth embarking on. So the kind of one starting point is that kind of if we don't assume that language, if we just grant that language models are black boxes, we end up in this kind of gridlock. And I think this is a place where we sometimes are right now in a lot of discussions, and historically, if you look at kind of debates on connectionism, you can see this end up. So what happens, we're thinking about these language models, these neural networks, kind of at the bottom, and the question is it possible to interpret these in higher level functional terms? So if we're thinking about language, we might be thinking about something like generative grammar, right? Is it possible for the thing that the neural network is doing to be translated into something like a generative grammar? And generally the assumption is no, like that's kind of where this debate begins. And then the irony is that the fact that the answer is no leads people to one of two extreme positions that are directly in contradiction to each other. So on the one hand, we get what some of my colleagues and collaborators and I were thinking through this, we're referring to as insulationism. This is basically where people say, because we can't understand these neural networks, because they are these black boxes that don't consist of any higher level kind of constructs, they're just by definition not a theory, right? This is not a useful thing to me if I'm trying to explain how language works and this thing is a black box and you tell me it produces language, but I don't know how it works. It's not useful to me, right? And then the other extreme is this kind of burn it all down approach, right? Which you sometimes get this kind of like radical connectionism, which is like, well, that's the whole point, because this neural network isn't obviously explainable in, like, it's hard to look at this neural network and say, where is the grammar or where are the rules? Since that's the case, what that means is that your theory is wrong and those things don't exist. And so this just completely eliminates the need for any of the kind of the theoretical constructs that we thought we needed. And this is kind of that Steve Panditosi article, right? That says that language models refute Chomsky. And so the kind of, my dramatic worst case scenario about this kind of world where we're treating them as black boxes is we end up in this gridlock where you basically get two camps that stop talking to each other because they've decided that they don't need to pay attention to each other's work. You have these insulationists who say, well, I don't care what's happening in LLM world because it can't really be understood. I don't need to pay attention to advances there. It's a fundamentally different scientific program. And then you have the eliminativists that are like, I don't need to worry about these theories that are happening maybe in generative grammar or in, Bayesian models of cognitive function or anything like that, because those people are like, they need to get with the times, right? They're just misguided. They haven't caught up to the new wave, which is LLMs for everything kind of. So I'm caricaturing quite a bit, but this is kind of the world you can sometimes fall into when we're looking at these language models as just fundamentally not explainable, right? But there's of course an alternative where we say they actually are explainable, and this seems, if we assume this is the case, it's incredibly relevant to how we're going to interpret these things, because for all we know, maybe the reason the language model is succeeding is because it has exactly implemented a generative grammar. So if you take something like Steve Panditosi's article saying this refutes Chomsky, and then there's a lot of details in that paper, but on, one argument is maybe not. Maybe you would go dig around within the nodes and you would find a full-blown generative grammar in there, and it would actually exactly support those kinds of arguments, right? That the only way to model language is to learn these kinds of structures. So without, if we assume that we're interpreting, that we can interpret these neural networks, then we can find this kind of, middle road where the existence of the neural networks doesn't completely wholesale replace the existing theories, but it can hopefully, we'll see some familiar components and we'll see some components that are entirely different, and that allows us to kind of inform and refine our theories and move forward. like I said, this can be a long-term research program. And so it's not just about like, let's find a compromise so that everyone gets along. I think that there's kind of several reasons why we're somewhat obligated to take on to make this assumption that neural networks are explainable and to invest effort in trying to explain them. The first is that just empirically, the language models are just good at language, right? Like they obviously make mistakes, and we've seen a lot of really good examples of the kinds of things that they're doing wrong, and I'll talk a bit more about those. But empirically, they're by like far and away the best thing we've had in terms of being the most human-like in terms of linguistic production ability. And so it just seems scientifically irresponsible to dismiss them without understanding how they work. Like we need to first understand how they work before we can make a call about whether or not they're relevant to the study of human language. Right? And then the second point, which I'll spend most of the talk on, is that it's actually just, it's a long game, but it's not that long of a game. Like we are not so far from being able to understand how language models work. And there's been a lot of progress and converging evidence showing that it's quite possible to explain parts of language models in these kind of higher level functional terms. And I'm quite optimistic that just even within the next, say, 3 to 5 years, we'll have enough of a grasp on how these internals work that we'll be able to start generating and testing, maybe even sooner than that, real predictions about things that might be happening in humans, and trying to kind of advance of what, are some of these bigger questions that we've been talking about here about grounding or understanding or meaning. I will say as a spoiler, because I've had this discussion a fair amount in both in trying to write and then talk to people, that typically when I say like, hey, we can interpret how language models are doing what they do, and then we can use that to inform and refine our theories of humans. People say, give an example where that has happened, and I don't have one, right? This is kind of a weird time. I'm very hopeful that in 3 to 5 years we have such an example, and then it'll be much easier to make the argument. We can say like, look, here's an example of the way that language models were handling, I don't know, I've thought about maybe noun composition, something we care about, and here's how it improved that theory, right? But I don't have it yet because it's a longer game, so there's no silver bullet right now. It's kind of a I would say I'm going a bit on evidence-based faith or something like that, right? But I would also be interested to talk more in the discussion about the trajectory and where we think this could be. All right, so I'll spend briefly a bit of time just arguing why I think this obviously language models are good models of language, and I personally like to talk about this just because I think in my career, especially like since grad school, like I think I originally was much more of a language model skeptic. I would have, and I've published a lot of showing ways that language models, fail to show human-like competence. And I've definitely like converted or changed a bit over the past, say, 5 years, just because of how slippery this kind of argument is. So I like to just reiterate the point that language models are, they're good enough to be taken very, very seriously from this perspective. So if we just like, despite their problems, despite the fact that we can prompt them in ways and get them to say stupid things, like if we just look at, where we were, say in the year 2010 or something, like the state-of-the-art language model was something like a 4-gram model that would look something like this. And then when GPT-2 was released, people were going crazy about how amazing this unicorn text was, right? This was the blog post where OpenAI was like, these models are too dangerous to release because the text is so good. And if you look at this, it's good, but it's not. But like now we're at this level that people say that we can't distinguish between models and humans. So we've just come an extremely far way in terms of just the quality of the text generation. And yes, they still make a lot of mistakes. I've myself worked a lot on this. We've heard a lot of examples from people through the summer school pointing out ways they get things wrong. But the gaps are closing. I always have this image in my head of this kind of the sad image of the shrinking iceberg, where if you're trying to find examples of things LLMs mess up, you have to get increasingly clever, increasingly nuanced every time I make slides. And I'm like, look, language models can't do logic or something. I have to work harder to contrive these examples, right? Because they keep getting better. And so the problems are going away for different reasons, right? And it's definitely not like, I don't want to say that there's like, this is the final recipe. I actually don't believe that this is the final recipe and there's nothing more to do in terms of building, intelligent systems. but it's hard to argue with the fact that like a lot of these kind of classic arguments we used to make about neural networks not being able to do certain things are getting harder and harder to make. And sometimes the problem goes away just because the models get bigger and it goes away. This happened for a paper that we were working on analogy, and we thought we had a paper written, and then the next big model came out and all our results changed. And every time the bigger model came out, we're like, okay, crap, we have to change our whole argument, right? I'm sure other people have had this experience. Sometimes it's because the models, the mistake that the models are making, if you go look at what humans do, humans are actually making similar mistakes. I think Gary Lupian gave really good examples of this kind of all of the, you know, noisiness and messiness of human behavior. And so it becomes harder and harder to make a kind of normative claim that the model shouldn't be acting that way when humans also act that way. And again, this has happened in our own work where we made some kind of claims that were critical of models. We followed up with humans and we found humans doing similar types of things. And then other times it's because you can kind of find these errors that the models are making, and then it turns out that if you look a little more closely, you can explain them in more principled terms. So we had like a paper that I worked on with Tal Lintz and Tom McCoy, where we were showing that models were kind of sensitive to these heuristics, where they were just basically looking at like word overlap and these kind of using spurious features to solve a task. And then we had follow-up work where there's pretty nice evidence that like their use of the spurious features kind of matched well with some information theoretic stories. And so maybe you couldn't like fault them so much for having used these spurious features, and maybe a decent model of human learning would have given a similar outcome, right? So the point just basically being that the models are very good, and even when they're doing things badly, I don't think that's a reason in itself to dismiss them as candidate models or candidate theories of human language and cognition. And so what I was, like I said, what I want to focus most of the time on is trying to argue that that the models are interpretable, and that we've made a lot of progress already in understanding them in these kinds of the kind of higher level functional terms that we typically want when we think about theories. And that if we kind of proceed down this path, I think we'll be able to generate kind of compelling, you know, predictions about how language works, or how aspects of language or reasoning or meaning or understanding or whatever our phenomena of interest is work. And then we can go follow up and, you know, work those philosophically or test them empirically in humans. And so I'm going to give a couple examples of some projects from our own work over the past couple of years. And I should say that it's kind of like, we'll go down like lower into just some specific phenomenon. And this mostly is kind of proofs of concept of what kind of representations and algorithms of the neural net's using. And like I said, doesn't have like an upshot for theories of language or cognition yet. So as a starting point, something that's been kind of a big shift for me is just kind of thinking about the transformer architecture as this more general purpose computer. So I wanted to just talk through a bit of the kind of general principles that we use for doing this kind of analysis I'm going to talk about. And I actually think that there's probably like just a lot of discussion to be had without looking at any of the empirical results, but just thinking about language models or thinking about the architecture in these terms when we think about the inductive biases of the transformer and its ability to carry out kind of complex computations. So the shift that, and I don't know if other people have this current mental model, but like when I started, I would think of the recurrent neural network, the transformer model, as a alternative to the recurrent neural network. So in the recurrent neural network, you have in your head this kind of words going from left to right, and the model is processing time from left to right, right? And so if you're going to carry out a complicated computation, it's going to happen like, it's like a meant to model, for example, like how I would model incoming speech, right? And if we're going to come up with, and we're going to have each kind of token representing a word. So if I have a many layer RNN, I'm going to have the tokens for the word cat. And as I have if I have a many layer RNN, I can get increasingly abstract representations of the word cat, you know, or whatever, increasingly context specific as I go up. Then the transformer is introduced and was explicitly introduced as an alternative to this by Google for engineering reasons, right? There was no like deep thinking about language or cognition that went into transformer. It's just designed to be efficient to train, right? But it gets rid of this recurrence and instead replaces it with self-attention, where at every layer you can look at every other time position with no particular bias towards words that are closer to you or further away from you. And when you zoom in on the transformer, each layer has these different blocks. So we have our words down here, they're represented by tokens. That's like my blue, those are like the word embeddings. And then you have an attention mechanism and then a feed forward network. And then you're at the representations of the tokens at the next layer. And you just stack up many, many of these blocks. And so this is kind of the guts of the transformer. And again, it was designed to be trained efficiently, but it has a few kind of key principles that weren't obvious to me until I started working on this, so I articulate them. One is that this attention mechanism, and we could talk more in details, but I'm going to just kind of assume that people have a somewhat working definition where you basically say like the representation, I don't know if people can see my mouse, but like this thing that says cats drink, like the representation of this token is going to be a weighted combination of the tokens at the previous layer. So maybe here, these dark arrows are saying that this word is attending to cats and to drink, and then combining them together in some way, right? And so since this is kind of an arbitrary, every token can look at every other token, what you end up, you can think of this as as each layer is like a set of registers. And then at the next layer, the model can learn a function for arbitrarily reading from those previous layers registers and writing to itself, and then it can send things downstream. So you have this kind of read-write mechanism that's taking place across layers, and that can pass information up the network in this way. And there's a pretty good description of this in this Olson et al. Blog post from Anthropic, where they talk about things like induction heads, which I think were alluded to yesterday. And you can find particular these attention heads that are very much taking on this kind of read-write operation, where they're, for example, copying in a content independent way, copying information across layers to be used in different ways as you move through the network. Then there's this second piece. So you have these attention heads that you can think of as these read writes, and then you have, these are interleaved with these feed forward networks. And what work has generally shown these feed forward networks do is they kind of pull in new stuff, right? So, so if you can think of and this is again, a very high level summary of what's going on. So there's a ton of nuance that I'm leaving out, but generally, you can think of the attention as reading and writing and moving around information that's already in context, and the feed forward networks as pulling in new information that's not yet in context. So maybe in this case, my attention has taken something about cats and drink and put it into this location, and then my feed forward network pulls in the information that cats like to drink milk and that they say meow and some other things, and then this together allows me to predict the word milk. So you have this fairly sophisticated, just even before you've really dug into it, you can just imagine what, like, people often talk about transformers as having like no inductive bias. And if you think about it in this way, you're like, that's a fairly rich set of things that are going on kind of in the architecture itself, that once it undergoes training, it gets even more sophisticated. But there's a lot going on here that you can imagine it taking, being able to carry out more advanced computations. And one of the big things that we'll show in these slides is that when you think about a complex computation taking place, really it's taking place from the bottom of the transformer to the top. So across layers, not across time steps as in the RNN, right? So when we're looking at a model that needs to, that is going to carry out some algorithm to do some complicated task, we can see that unfold by writing stuff to lower layers, reading from them, and moving up the network. And I think another important thing to observe is because of this property, once you've gone past the first layer, the content of these, what I'm calling registers, or the token representations in transformer, is actually fairly arbitrary. So sometimes people do this kind of analysis where you look at attention patterns and it looks random and it's used as evidence of spurious features. You say like, oh, the model is answering my question correctly, but it's attending to the question mark and not to anything useful in the sentence. And so that means the model must be getting this right by some spurious features, when actually it could be the case that that question mark token at this point by the final layer of the network actually contains a ton of very rich information that was computed and just stored there over the course of the earlier model. And we do see that kind of information migration. Okay. Oh, and then a final thing, which I'll make use of, is just that I'll talk about this again later, so I won't go into too much detail, but you can actually, you can ask the model at various layers as you go up to predict the next word. So you can kind of get this print statement type of a feeling where you can say, if the model was forced to answer when it's halfway through its computation or when it's all the way through its computation, or when it's 3/4 of the way, what would it answer? And it can kind of give you some insight into the way the model is solving the task. So I'll come back to this later. So my kind of brief takeaway just of kind of general things to say about the transformer is that you have these attention heads that you can think about as carrying out reads and writes across layers, and they can be viewed as arbitrary registers. And this is a really powerful mechanism that we actually, some of our studies were looked just at attention only transformers, and they're able to do fairly sophisticated things. You have the feed-forward networks, which can pull in new information, stuff that's not in the local context. And this kind of further amplifies the kind of work that the models can do. And we can get these kind of print statements, so we can actually like trace through the kind of algorithm or the, I like to think of it, the source code. That's Chris uses that phrase, the source code that the model is executing as it goes across the layers. Okay, so with that in mind, I was going to talk about kind of two sets of results, so a couple papers hanging together. The first is looking at some abstract representations of relations that I think kind of illustrates some of the key principles and things that we're looking at. And the second is looking at fuller circuits and their modularity and reusability, and how they can, and like what are the kind of building blocks that transformers are using. So I'll talk about each of these in turn. I'll start with this kind of abstract relations. So in this project, we were looking at how large language models, and when I'm talking about large language models here, we're working with open source models and fairly small models that we can dig into the network internals. So most of these results are on things like GPT-2 medium or large. They're definitely not of the scale of like, you know, GPT-4. And they're also and they're not even state-of-the-art models for the most part, right? So we're dealing with kind of simple models, but they are large language models. They're not toy models in this case. So we're looking at a simple task where we just ask the model, like, what is the capital of Poland? And it needs to say Warsaw. And we do it in this setting where we give a single example because we find that it just allows the model to stably just always predict a single word answer. Otherwise, it might say something like the capital of Poland is Warsaw, and it complicates our analysis. So the prompts to the model are something like this: what is the capital of France, Paris? What is the capital of Poland, Warsaw? And we're trying to understand how the model, like what representations the model is using to predict the word Warsaw here. And so again, kind of looking at this within the transformer, we have a representation that looks something like this. So we have a representation of Poland at some layer, and it goes through an attention and a feed forward net, and then it produces a representation at the next layer. And then at some point, we're at the last layer, and then we're going to read off from a language modeling hand. It's going to predict the word Warsaw here. And this feed forward network, and this is from some prior work. Did I? Yes, cited this. Giva et al. Giva does really good work in this area. Is basically just computing a additive update. So this feed forward network will take as input the current representation of this blue XI register. It's going to compute this vector, that's what I'm showing in red, and it's just going to add it to XI, and that's what's going to give us XI plus 1. So we actually just have a really, just by the nature of the transformer, a really simple computation that's happening here in the feed forward network to transform this representation of Poland across layers. And we're going to focus just on that little piece here. So this little O, what we're calling the O vector, and the work that it's doing, because we find it's actually quite simple in how it solves this task. So this is, like I said, this additive update going on here. And what we can see is we can basically say what word is the model predicting to be the answer as a function of layers. And we see this kind of phase, like these clear phases in what the model is predicting. So in the early layers, you can see that the model is predicting basically nonsense. We call this the kind of grokking phase, and we can speculate that we've started thinking about looking into it, although the student who was working on it is now interning, so it's kind of on pause, so I don't have a good answer, or I don't have concrete results on here. But there's this period where the model's not saying anything even topically relevant. It's just kind of predicting frequent tokens, right? And then it starts predicting Poland as its answer. And then all of a sudden it abruptly switches to Warsaw, and then it stays at Warsaw. We call this phase saturation. So there's this interesting period where we're saying this actually kind of looks like a function is being applied, or like a retrieve capital function is being applied here, where it surfaces the argument to that function, which is Poland, then it applies the function, and then it sticks to Warsaw. And this signature, so here the red line is showing the predicting the argument to a function for several. So we have a couple of relations. We have retrieving the capital city of a country. We have retrieving the uppercased version of a word, and we have retrieving the past tense of a verb. So these are all kind of like lookup table type functions. And how is it getting implemented? And you can see the red line is showing that the argument is being predicted. So in this case, something like Poland, and then the blue line is Warsaw. And you can see a pretty consistent, like kind of this crossing shape that across models of different sizes and across the different tasks where the argument peaks first and then the answer peaks. And it's usually around the same layer or the same percentage of the way through the model that this cross happens, which kind of suggests that the function is being, quote, applied. Another trend that we do notice is that this is kind of cleaner for larger models. So moving from left to right here, you can see the models are getting bigger, and you do see its effect is much better. For the small models, which are worse at the task, it's not as clear. And so what we can see is there's like this point, and so I think these next results are on GPT medium, say, so it's somewhere around like layer 19. There's this abrupt switch from predicting Poland to predicting Warsaw, or predicting, dance to danced or something for the past tense case. And it's happening at that feed-forward network. And so our question is this an abstract function that's being applied by this feed-forward network? And by that, I mean, like, is this a Warsaw retriever that happens to always happen in layer 19, or is it a get capital city function, right? And so if it's a get capital city function, what I should be able to do is I should be able to grab out this O vector that's computed when I give a prompt. So if I say, what is the capital of Poland? It predicts Warsaw. I can go jump into layer 19 and I can pull out just that vector that's computed by the feed-forward network at layer 19. And I can just plop it into some other context where the model was about to predict China. And this one doesn't even have anything to do with capital cities. This is a random sequence of tokens that are repeating, and China is the next thing in the sequence. So the model wants to predict China because they're very good at recognizing and repeating. And so what should happen when I put this O vector in is it should then predict Beijing. And if it does predict Beijing, that suggests that this is like a more generic look up the capital city, not a predict Warsaw type of function. And we find that, yes, that is exactly what happens. So this is for a single example where we're saying table mug free China, table mug free China, table mug free. And now we add in this vector that was grabbed from the example where it predicts Warsaw, and we see that it very strongly jumps up to predicting Beijing. And this happens in general. So we look at a couple different tasks that have this retrieval structure, and you can see that that we get these significant jumps in the predicting the kind of output of that argument. So suggesting kind of some modularity or some genericness to the way that this is designed. I will note that it's specific to one-to-one relations. So when we look at doing a similar thing where we look at something like name to nationality or animals to their hypernyms, we don't get an effect. So this isn't like an all-purpose relation retriever. It's specific to these like one-to-one lookup tables, right? And I think that's interesting, and we can talk about later, and when we're kind of thinking about where might we dig for kind of upshots that could help for improving our understanding of, for example, human language and cognition. It's also not used every time that models are asked about capital cities, right? So it's a mechanism specific to retrieving in this lookup table fashion in what we call the abstractive case. So here on the right, we say, what is the capital of China? And the model needs to generate Beijing. But Beijing doesn't appear anywhere in the context. In contrast, we can have an extractive case, like on the left, where you say the capital of China is Beijing. What is the capital of China? And here it actually just needs to copy Beijing from context. And what we find is that if you, what we could do is go in and just delete out the feed-forward networks entirely from this network to prevent it from doing this update. And if we do that, you can see that in the abstractive case, that's what's showing here, performance is very low. So this is showing if we just delete out most of the neural or the feed-forward networks, how good is it? And it's kind of a weird graph, but basically left to right is like, all the way on the left means you've deleted out all of the feed-forward networks, and all the way to the right means all of them are intact. So the point being the fact that these lines are close to zero, it means that if you delete out those feed-forward networks, the model is performing very poorly. But for the extractive case, when the word Beijing appears in the context, the performance is actually not hurt, even if you delete out a significant number of the feed-forward networks, which suggests that this is like a mechanism that the model is using but it's fairly specific. It's specific to retrieving these one-to-one relations, and it's specific to the cases where the model needs to retrieve from like in Waite's memory, not from in context. All right, so I'm going to pause for an intermediate discussion just because I have a lot of other stuff. I talk more about this, and especially the in context and Wait stuff. But I think the point I want to make with this is that we have this language model behavior, like answering what is the capital city of a country, and these language models are these massive nonlinear systems that have the capability of just brute force memorizing. Like, surely it can just brute force memorize the capital of China is Beijing as like a prefix lookup table or something like that. And it doesn't need to have any reason that has a relationship to a sentence like the capital of France is Paris. Like, those aren't, the model is more than capable of being the kind of pathological memorization machine, at least where this simple of a task is concerned. And yet we can find these fairly simple, fairly general mechanisms that show that it's kind of representing this relation in an abstract way, and that it's modular, and we can kind of grab it and plop it around and get the expected effects. It doesn't tell us anything about how language works, but you could actually start to imagine how even something simple like this might start to generate some hypotheses or some testable predictions that we could follow up on if we were trying to think about how humans carry out similar types of tasks. So, for example, there's something here about these differences between the attention and the feed-forward network and the in-context and the in-wait strategies that kind of echoes what we often talk about as like linguistic knowledge versus world knowledge. And I know, like, intuitively, we often say there's something about, you know, me inferring that a red car is a car, or that a blurpy DAX is a DAX, seems to appeal to something about the grammar and the syntax and semantics of language, and not about my lived experience. Whereas me inferring that like a brain surgeon is wealthy probably has very little to do with the syntax and semantics of English, and has mostly to do with, lived experience. And we have this sense that there's this distinction here. But in terms of getting at the mechanisms and how real is that distinction, is it categorical or a matter of degree, and what are the mechanistic differences and what are the implications for our grammars and our theories, that's the kind of thing that's pretty hard to solve. But we could look at language models that do this all the time, and we can say, how are they doing it? And to what extent do they use different mechanisms or the same mechanisms? And how do they know which mechanism to use? And you could start to pull out from the language model a kind of concrete, theory and description of how that whole messy system is navigated. And you could imagine that starting to contribute to some pretty substantive discussions about, how language works or how grammar works. There's also maybe something here about this kind of difference between one-to-one and one-to-many relations. I'm not sure. There's probably people in this room who know a lot more about how that works in humans, but you could imagine generating some predictions about how these relations are retrieved and seeing if there's similarities and differences there. I think another thing we've talked a lot about that's interesting here, and it came up a bit in Irina's talk yesterday when she was talking about the kind of making this huge assumption about the world being represented by kind of linear combination of principal components. I think a really interesting outcome of this project and many other projects we've done and many other projects other people have done is just how simple these like linear mechanisms in language models end up being. And maybe this says something about how like maybe the world is more linear, more simple than we think, and actually those kinds of models might explain a fair amount of cognitive processing. So I think there's some predictions in there to be followed up on as well. So just even just a simple proof of concept, and I'm kind of, taking it and running with it, but I think there's maybe a story where you can imagine using these kinds of studies on language models and pulling a lot of predictions and models out that could then really significantly advance the way we think about cognitive models and linguistic models. Okay, so in a kind of second set of studies, I wanted to, in some ways, go a little bit further. So these first ones is kind of like, here's a piece of like this add this vector in is like a really simple mechanism doing a very simple type of retrieval, but it isn't like the full story, right? There's obviously a lot of other things going on when the language model processes that prompt and answers the question that allow it to do this, like to figure out that it even needs to construct that vector and et cetera. So the second part, we've been looking more at these kinds of what we call circuits, or the kind of algorithms that the model is running across layers to solve simple tasks. And obviously, we're not the only ones working on this. So Jacob Steinhardt's group is doing a lot of really good work on this. Neil Nanda at DMind is doing a lot of good work on this. Chris Ola and Robotics and Morgi, but there's a lot of people doing really good work. I'm not naming all of them. So I'm going to highlight some of the stuff we've been doing in this area. So the kinds of questions we're interested in is like, what is the actual algorithm that the language model is using to carry out tasks? And then what I think is really interesting is like, what are the kind of core computational building blocks that those algorithms are composed of? Because you might imagine that in the way that we would look at something like, a programming language like Python or C++ or whatever people are using, there's kind of like a set of primitives that the models or that exist in that language, and everything is composed of those. And the same we would expect to be true from a transformer. It might not be a discrete, concrete set, but it's going to roughly, like, we're going to start seeing recurring motifs about the kinds of computations transformers can do. And if we can characterize those, then it becomes much more tractable to think about how are they going to solve new problems and what kind of mistakes will they make and will they not make. And of course, that opens up thoughts about thinking about relationships with humans. So obviously, if we can understand these building blocks, can we get insights into and control over language model behaviors? And hopefully we would hope this would provide insight into human behaviors. I guess I shouldn't have said control over human behaviors. I don't think mind control is anyone's goal here. Maybe it's some people's goal, but no, didn't mean to imply that's goal. So we'll look at two different tasks here in this next couple slides. So the first is from a paper from Wang et al. Group in Berkeley. So they were looking at this called the indirect object identification task. You get a simple sentence. These are all templatically generated, two names doing something, and then you get some sentence with an indirect object. So Robert gave a ring to, and the model is supposed to predict Matthew here. And then a second task, which is from a group from University of Pennsylvania, that has this basically, here's a list of colored objects, and you just have to retrieve the color of the object that's asked for. So these are two fairly different on their surface tasks, but simple language processing tasks. And so in this work by Kevin Wang and colleagues, they were looking at what is the circuit, like what is the algorithm the model runs in order to solve this indirect object task. And they found this simple circuit that I won't go into details how it's found just for time, but basically there's a series of attention heads, three key phases here. There's an attention head at an early layer that recognizes the duplicate name. So it says it recognizes that Robert's duplicated, and it basically passes this information to a subsequent layer to what they call the subject inhibition head. The inhibition head then blocks attention to these names, to the duplicated name. And then it talks to what they call as the mover head. And the mover head, basically all it does is attend to names and copy them into the output. So without the inhibition head, this mover head would attend to Matthew and Robert and maybe predict Matthew or Robert at equal probability. But with the inhibition head, it can't attend to Robert, so it just copies Matthew. So that's like a very basic algorithm, but that appears to be how this GPT-2 type model solve this task, because they recognize the duplicates, inhibit the duplicate, and copy what's left over. Okay, so now we're going to look at this new task, this colored object task, which is a very different type of task. And we're going to also ask what kind of algorithm is the model running. And what was very interesting and surprising to us initially is that is overlapping, the algorithm that the model uses overlaps in a significant amount of a significant number of places. So the exact same duplicate token head attends to the duplicated word here, sees pencil. Then there's actually not an inhibition phase, and I'll come back to this in a second, but instead there's what we call content gatherer. There's a prior work, which I forgot the citation, but I'll add it in, that gives them this name, content gatherer head. So basically that promotes attention to the duplicate rather than inhibiting attention to the duplicate. And then there's a mover head that attends to the colors of the nouns and copies, right? And so you end up with these two highly so in kind of 2 out of the 3 phases, these circuits are the same, and they differ in this middle phase, where the IOI task is using this inhibition head and the other is using this gatherer head. But the interesting thing also is that the GPT-2 large, which we're looking at here, is excellent at the IOI task, at this Robert gave the ring to Matthew task. It's at perfect accuracy, and it actually just really sucks at the colored object task. It's basically at chance. It's just randomly guessing between the colors. And so there seems to be something that went wrong here where the model should be using inhibition, right? Like it needs to inhibit these other colors, but it's failing to do so. And so what we find is we go and look at what this inhibition head is doing, because it's the same model, that head exists, and see what it's doing during processing. And you can see it's actually, it kind of knows what to do. It's attending to the colors, but it's got very weak signal. And then there's this other kind of inhibition head that's basically just attending to the start of sentence, which means it's behaving correctly, it's inhibiting what it attends to, but it's what we call benched, right? Like this is basically sometimes when models have attention heads they're not using, they just all attend to the start of sentence. And so what we can do is we can do a really brute kind of proof of concept intervention, which is force the attention of this inhibition head and the name mover head to attend to the wrong color names. And the point of this is to show that this thing is kind of modular and reusable, right? This inhibition head, if we just change its attention pattern, then it will plug into the rest of the circuit in the expected way, and it will prevent the mover head from moving, and therefore, or from moving those incorrect colors, and therefore cause the model to give the correct answer. And so like I said, the model is good at IOI, it's bad at colored objects. When we force this intervention, you can see that it actually almost completely recovers to a perfect accuracy on this colored object test. So again, kind of proving this point that these components are reusable, and that they serve kind of these content independent types of functions that can be called in, like invoked across different tasks. And I'll talk a bit on the end of speculation, but I think kind of well, I'll talk about them in that discussion. So I want to follow up a little bit, and this is some kind of new results since last time I talked about this. So just digging deeper into this inhibition, because this inhibition component is quite interesting. It does a lot of work, and it seems to be quite general. And it seems to be implicating other kinds of model behaviors. So we're looking, just saying, let's look more at inhibition and where it's active. And if we just like looked at when this head is active across corpus of natural text, it seems that it's active anytime there are lists of lists very broadly defined. So my student Jack, who's done all of this work, so, you know, like in a kind of and separated list, like John and Mary, this head is active because that's like a list of 2 items. If you have a list of objects like blue pencil, black necklace, yellow lighter, it's active. It's also active if you have like a bulleted list, or if you have lists separated by things like but, or, you know, semicolon, so longer form discourse. So it's a very general active when you see lists that are activated. And so you can imagine that anytime you see lists, there's a role for kind of inhibiting and allocating attention appropriately. So it's allowed to look at a different list task where we call this the laundry list task. So here you get just an arbitrary list of items. The model says, so tonight I go to the store, I'm going to buy a plate, a pear, and a pen. First I will get the pen, then the pear, and then and it needs to fill it in. And so the point of this task is you have this list of items, and then they appear in a random order. So you need to be able to recall a random item from the list. And this is an interesting task because it's pretty simple, but it starts to show some interesting things about the transformer that might not be obvious from the architecture itself. So one is this kind of sensitivity to order, right? So if you ask, and this is kind of a specific instance of a general frustration or problem we have with transformers. And I think Gary also talked about this, that humans have similar sensitivities, right? So like, if you ask about the plate, the pen, the pear, and then the textbook, the model does great and it finds textbook. But if you ask about the textbook, pen, the pear, and then it doesn't want to say plate, it says textbook, right? So like it can retrieve some items from this list, but not other ones. And this is interesting, I think, because unlike an RNN, like the transformer is supposed to have kind of, you know, there's no real privilege to some positions over the others. There's no reason why self-attention should be worse at attending to textbook or attending to plate than to textbook. So there's something kind of emergent going on here that leads to this instability. And similarly, we see this as the number of objects in the list gets higher and higher and higher, the performance drops off dramatically. And once again, like unlike an RNN, a transformer is not really supposed to have this type of sensitivity, right? There's no reason that self-attention shouldn't care how many tokens it's going back over, right? This is a very parallel or kind of symmetric process. So we want to understand more about what's happening within the mechanism here that might explain these kinds of behaviors. So we're going to look specifically at the communication, and like I said, I'm getting kind of into the weeds here, but I think it's an interesting illustration of the kinds of representations that models use and how this affects behavior. So we're looking at the communication between the inhibition head and the name mover head. Basically, when the model has decided to inhibit something, I can't place my emphasis. When it's decided to inhibit something, how does it communicate to a subsequent piece of the algorithm what to inhibit? And so what happens here is there's this kind of circuit going on here between the attention heads. There's the keys and there's the values of the inhibition head, and there's the keys and the queries that are talking to each other. So I won't go into the details, but there's basically, this is being mediated by a matrix, which we can decompose down into principal components. And if you look at these individual components, you can find that there's one dimension in this space, and the items are being placed along this dimension. So you can see this one line in this kind of what we're calling our communication channel between these heads, where one side of this line says you should inhibit the first item in the list, and the other says inhibit the second item in the list. So if you have this John and Matthew, or John gave a rim to the Matthew, like one extreme is saying you should inhibit Matthew, predict John, and the other extreme is saying you should inhibit John, predict Matthew. And so you can go in and you can intervene here, and you can get a pretty clean modulation of what the model attends to and then predicts. So you can basically just scale up this component like you have a knob, and you get a pretty smooth transition here from attending to John predicting Mary versus, or I guess inhibiting John predicting Mary versus predicting John. And it works very nicely in cases like the IOI task where you have 2 items in the list, or the laundry list task when we have 2 items in the list. But then what happens as you add more and more items is it still wants to keep using this same mechanism. And so it seems to just keep overloading it. And so it'll reliably be able to pick out one item in the list, but it won't be able to pick out the other items very well. And so as that starts to happen, you can see that you can start to imagine why it gets worse and worse at attending to certain items. And so in particular, it's very good at inhibiting the first item in the list. It's much worse at inhibiting subsequent items, or it can't reliably differentiate between the subsequent items. We found a kind of interesting point here, and I'll talk a bit about it as like with scale, but there's multiple of these inhibition heads, and they all have these different dimensions. And so really, if you look at 3 of the inhibition heads, you get this nice 3D space where you can uniquely pull out individual items in the list. So if we have 3 heads and 6 objects, and you look in this 3D space, like it is possible to uniquely select or uniquely inhibit single objects. And what we can do, again, is we can force intervention by forcing the model to position its head such that it's at a specific place in this space, and you can significantly improve accuracy again. So there's this kind of disconnect where the model is kind of capable, it's representing distinctions, but it's not necessarily harnessing them all the time. But you can start to see a connection between the way the thing is being represented and the kinds of errors and instability that it makes, and the kind of prompt sensitivity that you might have. So I'll kind of summarizing these things together. So I think that kind of the main takeaway from the second half stuff is just that we have evidence already emerging that there's kind of these individual circuit components, and they're fairly modular and generic. They're reused across tasks. You can go in and manipulate them and get the kind of expected effects. So it's starting to look more like a kind of a symbolic architecture than we might typically think with an LLM. And this starts to give us some insight into the kind of building blocks of transformers, right? So obviously there's a ton of task transformers too that don't look like these toy ones I'm doing, but just even the fact that that we see this kind of reusable components across many types of things suggests that maybe there's some, small-ish, finite number, much less than the number of parameters in the transformer, number of little computational units that transformers are capable of learning, and they're going to piece these together in certain ways. And they don't necessarily match our intuitions from linguistics about how a task decomposes into tasks, but it might generate new kind of interesting theories about how this could work. I think it's important to show that you can mend these broken circuits and affect performance, because that does suggest that they're like not just like these kind of epiphenomenal weird things, but we can actually kind of go in and they plug into the plumbing of the system in the expected way. And there's a lot of kind of work in progress that we're interested in and kind of currently working on, but I don't have concrete results on. So one is kind of like, I think relates to the discussions we were having yesterday and the Arena's talk of kind of the relationship between these mechanisms and scaling. And I think sometimes what we see is that when the model has a good representation, like was the case in the inhibition examples I'm giving, but it's not using them, and then we intervene and make it use it and it works. What we might be seeing is kind of an undertrained model. And as you get larger models, it will eventually figure out that it can use this stuff that it has lying around for this other task, right? So we're working with fairly small models, but possibly as we get bigger and bigger models, we would see that. And so that's something we're interested in looking at. And then we're also thinking a lot about the similarities to human neural mechanisms, because some of these properties that we're looking at here actually do call to mind things we think about in the brain. So for example, this inhibition mechanism that's collapsing everything down into 2 dimensions or into 1 dimension when it's capable of doing much more than that, is interesting, because we might have this kind of notion of capacity limits that humans have that transformers don't necessarily have, but we see that this emerges in the transformers anyway. This could tell us something about why we have capacity limits and kind of what's the value of them, and what are some of the trade-offs we might get there. So there seem to be connections to some kind of working memory models and recency biases, some content effects, some curriculum effects. So I can talk more about these things in the discussion. All right, so I'll just wrap up saying the same things. Language models are often assumed to be black boxes. I think that's just a wrong assumption that we need to not take for granted. That if we interpret them in higher level functional terms, we might get insights into kind of the cognition of the language models, and that might actually give us insight into cognition of humans. I think it's a long game. Like there's work to be done. Like our methods for analyzing language models are kind of brute and coarse, and so there might be several years of just methodological work needed before we can get like the really good insights we need. But I think if we're in work in progress, and I'm optimistic, and I think if we keep working on this, there's kind of 2 outcomes that happen. This is why I feel like it's unlikely to be a complete dead end, because either we get some explanation of how language models work that at least in some ways is human-like, and I think at some level of analysis, and this really is what I'm hoping is happening and is really exciting in terms of, adding kind of empirical rigor and something to like sink our teeth into in some of these discussions about things like understanding or consciousness, right? You're like, we'll have a concrete thing to look at. We'll say, here's how it's the same, here's how it's different, and we can talk about that rather than having to do kind of a thought experiment. But there's also the possibility that we invest all this effort and the language models are just absolutely in no way at all human-like, right? It's just like, it turns out the whole thing is a lookup table, or it's something that's just ridiculous. But even if that's the case, then there's some kind of, like we've talked about the kind of things like predictive coding and the information theoretic pressures. Then we kind of owe a story for why humans didn't converge to this other solution, right? Like what are the critical pieces? So I think that could still advance our study of language more generally, right? Like we now have 2 kind of alternative paths to the same intelligence in some ways. And I think that's an equally interesting position to be in. All right, so with that, I will stop. I'll put on my collaborators' lovely faces again, and I'm looking forward to discussion.
Thanks a lot, Ellie. That was terrific. Clapping ensued. And if anybody didn't rethink what they thought about what these LLMs were doing who hasn't heard this talk, you're not really listening. Okay, that was terrific. Now, hold it.
Okay. May I share my screen? Just
Please.
right. Yeah, I think that it really was terrific, Ellie, and so rich, so much information, far too much for me, I should say. So I thought I'd focus on a very general point of view and a very general thing. Actually, the general remarks that you make in your recent paper, can DNNs inform cognitive and psychology theorizing? Well, And in that paper, you that was the beginning of your talk. You distinguish between the skeptics and the enthusiasts about neural networks, and say that these are extremes. Indeed, they are, if they come up with these claims that either DNNs are useless for cognitive science, you call them insulationists, or that existing cog size at the end of the day useless. This would be eliminativism. Whereas you think that we can interpret DNNs and thereby inform cognitive science, surely. This obviously touches on the issue of reductionism. As a philosopher of science, I get reminded on that. And so I thought, okay, how is that? What's your take on this? Can high-level cognitive science, sometimes also sort of boxology that we see there, be reduced to low-level neural computation, or rather the implementation? You also sometimes say things like, can higher levels play causal roles? I want to compare this to other reduction scenarios, just one, if I'm allowed to. There's the standard case in the reduction debate that came up by Nagel already in his classic piece on reduction and theory reduction. The idea that, okay, classical thermodynamics had been successfully be reduced once to statistical mechanics. Classical thermodynamics considers all sorts of macro properties. So it does high-level theorizing and modeling with entities and properties like volume, pressure, temperature. Whereas statistical mechanics then comes along and replaces the entities. It no longer talks about gases and their macro properties, but talks about molecules, and they have position, momentum, energy. So no talk about temperature any longer, for instance. So that's low level. There is the almost canonical model of reduction is the Nagel-Schaffner-Hooker model. The idea of the model is once to say, well, in a phrase, to reduce is to deduce laws, which is to say, take the higher level regularities. If you are able to deduce them or construct them out of the lower level ones, that's successful reduction. The problem, of course, is as the vocabularies of the two theories, the high level and the low level, differ, we need correspondence rules or bridge principles to bridge this. An example of a correspondence rules in the case of the reduction of thermodynamics would be, for instance, very often used, the idea, okay, temperature then translates into mean kinetic energy of molecules, for instance. Okay, typically, of course, this kind of correspondences would be far more complicated than that. But in principle, we need them. Otherwise, we cannot translate the vocabularies of the high level and the low level. Cognitive scientists talk about very different things than people who look at neurons and their properties. Just following up on this one slide longer. There are problems with reducing, for instance, the laws of thermodynamics. And when it comes to the second law, which is the notorious problematic case, which talks about entropy increase and strict irreversibility, it turns out that you cannot strictly reduce this law. You can only recover something that is close to it, sometimes known as the eta theorem, which talks about entropy increase only statistically and has no strict irreversibility recovered. Or for instance, also modeling that we find in high-level thermodynamics. The idea of the ideal gas law is, if you look at it, is literally false. There are no ideal gases, nor are there infinitely many point-like molecules or something. So strictly speaking, you could think reduction seems to fail. The Nagel-Schaffner-Hooker model says, okay, it's not necessary to aim to strive for strict reduction. It's okay to approximate the high-level theory or model by some low-level image or some analogous image that's built out of the low-level stuff. So a high-level image theory that can and must be constructed out of the low-level theory or model. The fun thing is you don't need any longer bridge principle because you now have a theory that is based and built out of the theorizing and models of the low level. Okay, if we compare this to your case, the low-level theory would be the neurocomputational models of DNNs. The high-level theory would be the models of cognitive science, psychology, blah, blah, blah. The high-level image theory would be interpreted DNNs. Precisely the work that you're doing. Now, some of the high-level regularities, I suppose, will not be strictly reducible since they only hold approximately. Compare the second law. For instance, I mean, and we know this from psychology. I mean, are there strict laws in cognitive science and psychology? Probably no. I mean, if only a few. They typically don't hold universally. They have exceptions, and they include many approximations and idealizations. And when it comes, for instance, to language, the assumption that there are infinitely recursive sentences that we can grasp and manage, for instance. So now my questions. The causal power then, if I take your view, the causal power at the end of the day is carried by the low-level realizers of whatever goes on in my high-level models, which is to say, of course, it's at the end of the day what the neurons do and what is encoded in the weights. This is all there is in the brain or in a neural network, in a deep neural network. So deep neural networks and their interpretations along your lines seem to call for, I would say, eliminative ontic reduction of high-level cognitive entities, because the causal power is in what the neurons do. But you might think of it as a conservative reduction of the high-level terminology, which means that many cognitive science models are still practically useful and provide useful approximations. So at the end of the day, the view that you propose is neither insulation nor eliminativism, but actually instrumentalism, which is, I think, good and fine, but I wonder what you think about it.
Thank you. Yeah, this is great. And I'll give my thoughts and you can tell me if I talked past any of your more direct questions, because I think, yeah, like in some sense, it's like if we take what I'm proposing, we're saying we're going to explain things in terms of the neurons and the weights in the model. And so that sounds kind of a limited B. And that's where the causal power is. And you can tell me if I'm misinterpreting, but like in my mind, something like, I feel like the causal power often is at a higher level. So when we, like in the examples I'm giving, it's like, you know, they're not perfect, but we say something like the mover head, right? Like the mover head is, it's like a group of neurons that is behaving together in a particular way. And that's the thing that has kind of causal force. So this is why I say like we don't have the silver bullet, because like that example is not satisfying to me, but I can imagine a similar one where you're going to say, okay, I have a similar, like I have this group of neurons that are working together and it is representing like a constituent in a parse tree, right? Like it's now this thing. And yes, there are individual neurons that make it up, but truly one would feel pretty good saying this is a neural implementation of this constituent, say like this thing is representing the constituent. And that thing has causal force. And the thing that's where we kind of in this paper call it like informative implementation, or maybe it's instrumentalism, is like for many things, for a ton of phenomena, a ton of behaviors, it might be completely irrelevant that that constituent is implemented in neuralese. You would have done just as well with your existing theory, right? Where you're kind of, what did you call it? Boxology or something, right? It's like just this is a constituent, treat it as a constituent, and but there are definitely cases where it doesn't, right? Because no theory, including the current higher level theories, is perfect. And so there's these places around the edges where the way to explain, you know, the weird content effects that humans have, or the reaction time differences, or the prototypic or whatever, actually, when you appeal to the implementation, now you can explain that in addition to having the power of the higher level thing, right? So it's like it's definitely true that some, like you don't always need to appeal to the implementation, but what the neural net, like the LLM, I think provides is the ability to have the high level theory paired with the implementation, so that when you have phenomenon that you've hit the end of what you can explain with your high level theory, you can just cleanly appeal to the implementation and hopefully be able to explain those effects, right?
Yeah.
I think that's kind of the dream. So I don't know, to me, it doesn't feel like a limitivism, because I feel like, you know, even in these little tasks we're doing, it's like we're going to talk about the inhibition head. We're not talking about a single neuron, right? So it's already kind of a higher level construct. Or we're talking about this vector in space, or this linear addition, or this point along a line. Like those are
all these. But isn't it true that all these entities that you come up with now, these high level entities, have their causal power in virtue of being constituted and built up by neurons and their weights and whatever the causal powers of the neurons.
I think so, but there, like, I guess we don't have enough about the thing, but there might be the kind of thing where it's like you can't tell this story with anything less than all of them together, right? So just like you, I would need to think about this a little bit more.
Okay.
But there might be, there can very well be something that it's not I'd have to think about that more. I think I might.
Many people have raised their hands. Maybe they want to.
Yeah.
Okay, Gary.
Oh, thank you, Ellie. That was great. That was terrific. And I haven't seen your previous talk on this, so a lot of it is new to me. Yeah, just as a quick reflection, I don't think there's anything in cognitive science that I'd be comfortable calling a law. There's such a gap between biological and psychological sciences and physics. That and it's not just because cognitive science or psychology is a new science. I mean, it's been around for quite a while. It's just, I think the systems don't lend themselves, at least for right now, to anything like laws. And so, what we have are lots of empirical observations and generalizations of those observations. So attempts to unify seemingly disparate things, but those unifications, I don't think, have the property of laws. And so the kind of research program Ellie describes is very much analogous to Connectionism's research program, right, where you have ideally kind of an iterative process between the modeling enterprise and the experimental human or animal enterprise, where observations of the organisms raise questions that you can often answer in a more satisfying way or in a more rigorous way using the model, just because you can intervene on the model much more effectively. And then the model behaviors suggest new ideas, new questions, new hypotheses that can be tested experimentally. And so that's actually like my question to Ellie, whether these investigations of the model behavior have led you to are there questions that you want to answer experimentally as a result?
Definitely. I mean, I would say some ways, when I say it's a long game, I think when I start, during my PhD, I worked on paraphrasing and more formal semantics kinds of approaches. And I actually really enjoyed your talk because the kinds of things you were describing is I was doing a lot of crowdsourcing and collecting human paraphrase data and stuff. And it's just so frustrating how humans just don't, there's just so much mess and it's noise. And then you're just why is this noise? How are we deciding what's noise? Eventually our model is going to need to account for this noise, right? So I think that those things are interesting to me. And to me, this is a really long path to kind of getting back to some of the, some of the kinds of things that I think are really interesting that we work on is noun and adjective composition and things how do you decide whether a blue dog is a dog and whether a fake gun is a gun and those kinds of phenomena, right? Just how do you, what kinds of inferences do you make, right? You get some sentence and you make some inferences and some of these are definitely entailed and some of these are common sense and some of these are pragmatics, and that becomes this whole messy world of when I hear some sentence, I'm going to infer a whole ton of things, and are they all coming from same mechanisms or different mechanisms, and which ones are revisable and which ones am I committed to, right? There's all of these questions in language and semantic theory, and to me it seems like language models should be able to generate some nice predictions about those, where my feeling is that you would get something that would have pieces of it that look familiar given the semantic theories that are out there, right? It's not going to be nothing in here is at all recognizable. Like there's nothing like a set of, you know, lexical entailments, right? It's like, or there's nothing like a kind of Gricean inference happening, right? Like you would be, I think you'll see pieces that are familiar, but then exactly this, there will be some pieces that look kind of different or depend on the implementation, or you can see these bleeding content effects that make it, that help explain why this slightly different context causes it to be entailed here and not entailed there. So that's kind of a vague answer, but yes, in my mind, I think it'd be really nice to go back to just some of these natural language inference questions that I've always been interested in, but I think there's a lot of phenomena that would help. But language and inference feels like the right place to start because they are language models. So they seem more ripe for harvesting those kinds of insights than, you know, maybe some other things.
Okay, we have a lot of questions, so let the questions be short and also the answers if possible. We have Steve, then we have Dennis, and then we have Eric, and then we have Anna. Go ahead.
Hi, Ellie. Nice talk again. I really enjoyed it. I had two quick observations and maybe a hard question. Maybe you could just answer it by saying no, which would make it short.
Well, I was told to give a quick answer. So
I don't want to answer, right? Either way. The first observation, illuminativism, was something coined by Steve Stitch back in the 90s, colleague here at Rutgers. And it was really, the connectionism was in the position of trying to rewrite folk psychology. And so he had written a number of papers. Now, on the other hand, Zenon Palishin and Jerry Fodor, who were here at Rutgers, also spent a lot of time trying to eliminate connectionism. So there's another term you can pick in there. So one other observation is the very interesting thing you showed about inhibition, and that the LLM just preferred to, you know, basically get worse as you got more in. This sounds a lot like working memory to me. I don't know how you frame it as such, because these heads are so interactive, and it seems hard, at least for me, to factor everything out. And if you see something that has this emergent working memory property, that's it's amazing. Okay, so here's the hard question. That was just no way to, you don't have to answer that one. Anthropic and people like Neil Nada, and there's a whole bunch of other people, and they're obviously doing similar things to you, and they're creating these big circuit libraries. Do you, I assume you people all get together sometime in a tea party and try to figure out if you're, well, I invented that, I found that last week. No, you did. And so trying to sort that out. It strikes me that this is very similar to my neuroscience friends, who often use the phrase, it's going to be a long time before we sort this out, sort of like what you're saying. And there's a sense in which when people say that, I always think 43 centuries, because there's so many things, right? 3 to 5 years seems like a short time to me, but maybe because I'm old. But the whole thing is that this could just never, ever converge.
Okay, question posed. Go ahead.
Yeah, no, I mean, I agree. I think a question I was going to ask actually in some other talk, it's like, I don't think you have to end one program before you can start the next. So that's where my 3 to 5 years come from. Like, I think we would be able to generate, like some of the stuff I was just talking about, Gary, I think we could generate some predictions about aspects of human processing based on parts of circuits. So working memory is actually exactly, I'm working with some neuroscientists here for exactly that. Like, okay, we've got something that looks kind of like working memory. What are the normative conditions under which it emerges? Could that tell them, like, we could start looking at that. Meanwhile, while we try to fully sequence the human genome and fully sequence the LLM kind of a thing, right? Like, it's not like you have to have fully explained the LLM to get anything of use out. So I think I would imagine them happening in tandem. So maybe it will be 43 centuries or whatever you just said to do the full thing, but hopefully we get insights.
Okay, I'm going to preempt the order because Friedemann is a panelist. Go ahead, Friedemann. Friedemann Pulvermüller, turn on your face and speak.
Yeah, now it works. Can you hear me now?
Yes,
Yes.
fine.
Yeah, something was not working. Yeah. Thank you for an excellent talk. And may I ask you to explain more what these very interesting entities actually are, and are and do. For example, inhibition head or mover head, as you mentioned. Well, these are groups of neurons, right? In the and what how do they get connected with what, and what how do they know, how do they learn where to direct attention, in a sense, or
Yeah.
what is that if they direct attention?
Yeah, that's great. I thought I had a backup slide on it, but I don't. I think I deleted it because I don't know why. But yeah, so the kind of the transformer before any training has this self-attention that's this key query value attention. So basically each token is associated with 3 vectors, a key, a query, and a value. And what's built into the transformer is that keys and queries, like you dot product between them to get a number, and that number will tell you how. So if I'm sitting here as the token for the word, say Warsaw, right? My query will dot product with every other word, with every other word's key to get a scalar value. And that tells me how much I'm going to attend to every other word. And then I'm going to multiply those by the value vectors, and that's what gets passed forward. So then my content at the next layer will be those scalars multiplied by everyone's value vectors passed forward. That's like kind of the attention mechanism. And so once it undergoes training, it specializes. Some of them will specialize to do things like attention. Oh, I should say a head is like, then there's like, if there's 96 attention heads, there will be 96 keys, 96 queries, 96 values, right? So one of these heads might specialize to be inhibition, which means that if you have a kind of a high attention with this head, it's going to pass forward a value that says, don't write me, right? Or it's going to block attention by specializing its key so that you don't attend to it. Like there's different ways that like you can specialize that mechanism to achieve inhibition. And so there's the kind of interesting thing about like the transformer is it actually builds in a ton of machinery for this attention and the writing forward of stuff. And then after going training, it's actually not too much work to say like, oh, the way this particular head wants to use its keys is to prevent, like if I'm a duplicate, I'm going to prevent attention or something like that. That's kind of felt a little hand wavy without like a whiteboard or something, but I don't know.
Okay, yeah. May I ask just a follow-up question, which is now, but this must be, if you say it connects with one item, it's one part of the input string, not one part of a lexicon somewhere represented separately. So for example, the word to the left of my noun, my critical noun, usually the adjective, you would then put attention on that one, and later on you can use this in a to retrieve the right color. But this is very shaky because you could say, for example, the red warm cup or something.
Right.
Then it's not the next, but the second next, or even the third or fourth next. So it's pretty shallow. This would indicate a rather shallow understanding, and it could be easily fooled. Is this so that you can fool it like this?
Yeah, we didn't play around with that a lot, but so there's many attention heads that are going on, and they're taking place over many layers. So this is where I was kind of saying, like, this computation takes place over layers. So what I think, not in that particular example, but in similar ones, what you might sometimes see is basically there's a lot of movement during like this maybe grokking phase where basically every token is kind of recording relevant information about itself. So there might be an attention head, and there probably is an attention head in GPT in the GPT series that is basically effectively doing a lightweight dependency parse, right? So it's basically specializing to go find the modifiers of a word and write them to itself. So like in those first couple layers, you might see all the nouns saying like, go find your modifiers and record them onto yourself, so that by layer 4 or something, anyone who attends to pencil already knows that it's blue and it's in the whatever. And so maybe some of those heads just look immediately to the left, but others might be a little bit more specialized so that they're better at looking further afield and kind of tracing the question. Of course, that requires it. So those can take a couple layers. What we have found, or kind of we have a theory, I don't think we have like a really good evidence. It's like if you make the kind of task complicated enough that it has like a deep computation tree, you might suck at it because it just runs out of layers, right? So it's like doing the right stuff and it's prepping, but it's like too nested, right? Like, so it just doesn't do. But yeah, so I think you could trip it up, and these are the kinds of things we'd like to be able to do. If you could really trace the mechanism, you should be able to trip it up, but we didn't do that exact thing. My guess is it'd do pretty well because the pre-trained models have a good like dependency parser in them.
Very good.
Thank you.
Next question is Dennis Erno.
Great. Thank you.
Thanks.
Thank you. Exciting talk, many interesting topics, very convincing. One question is, you suggested that understanding large language models can help us understand language and human cognition also. But you focused your whole discussion on transformers, and neural mechanisms in the human brain are very different. So as you mentioned earlier, transformer was proposed with goals of computational efficiency, no cognitive considerations at all. And there is no direct analog of self-attention in human brains. There is no analog of transformer-like sublayers in natural neural systems. It's not even clear if language is represented in the brain in something like a sequence of embeddings, which is crucial for transformer architecture to work at all. What are your thoughts on this? Would it be better maybe to study modern versions of recurrent neural networks, which were proposed with cognitive underpinnings in mind, such as XLSTM or WACU? So please share your thought on this.
Those are great questions. So I'll admit I'm not a neuroscientist. I've been trying to learn more and started working with neuroscientists mostly in the past year or so because I'm pretty interested in this. So perhaps there's no direct analog of self-attention, but when we've been looking at the working memory question specifically, we've been, at least the neuroscientists I've been working with have been excited about actually the kind of similarity between the self-attention and existing computational models of things like selective gating and like stripes in memory and stuff. So at least their take, or from my discussion with them, is that this is not completely biologically implausible. Like it's not like a dead end, right? So there might be something valid to it. So I think that's part of it. Another part, something I'm very interested in, I think maybe this is related to what Cole was saying, it's like kind of the emergence aspect, right? So the working memory, this kind of weird capacity limited working memory is a really good example. Like the transformer doesn't have that built in, but something about training results in it being there. And so that maybe provides a really interesting way to think about what kind of like pressures from the environment might result in specific architectures. So from that perspective, like if we find circuitry in the transformer that might resemble parts of the human brain, even if it wasn't designed to be that way, but it emerged that way, then it can provide an avenue for thinking about maybe whether similar pressures could be, like maybe that's why the brain is how it is over evolution. Maybe this is why we have this particular type of thing. So like and we're gonna run out of time, but like we even kind of have some evidence of like kind of emergent recurrence, right, in the transformer, and that's interesting. So it's like, oh, this recurrence kind of shows up. It's like a hacky version of recurrence, right? It's like repeating stuff across layers because it might need some stuff but you can imagine those kinds of things, right? I mean, a transformer is not entirely unconstrained architecture.
We have to go on to Eric and to Anna and then stop. Eric, very short.
Yes, I think I can be very short. Ellie, fascinating talk. Even it's a great research program, I believe. My question concerns your object of study, the various types of LLMs, which of course keep changing, and the modern ones, we don't even know what they are because they keep constantly changing. And one question I have is, they are not only models of language; they also represent for example, commercial interests, because they exclude, for example, nowadays certain topics. And then there is the question about which languages have been used in training them. So are you still confident that this doesn't matter?
That what doesn't matter,
The commercial interests, which, for example, excluding all sorts of topics, the differences in the languages that are used for training.
I think it 100% depends on a given project and or even research question. So for example, if I'm trying to say, look, something about predictive language modeling leads to capacity limits in working memory, I don't feel like the omission of certain content from the training data interferes with that conclusion, right? Like that feels a little irrelevant, right? If I was trying to draw some conclusion about like, language model and other points we've worked on something like grounding, right? And we're saying like language models can learn about color space. Like it's pretty relevant what data they were trained on, right? Like how, like conclude. So I think for certain types of questions, it is 100% very important what it was trained on, and for others, it doesn't matter, right? Like it just matters that it's a language model. And so I think it's very much on a project by project basis. And I don't think for the whole research program, there's a one answer, right? It's project by project, and hopefully it's fine.
Thanks, Ellie. Anna, super short.
Okay, I have a similar question. So I have the impression that your patient is a moving target. It's changing every day. And then I wonder, how do you compare the results of your colleagues? So you investigation patient 1, but your colleagues are maybe already investigating patient number 76. And how can you compare the results?
Yeah, I mean, I guess, well, so twofold. So one is we generally use these open source language models like GPT-2 small or something, which aren't like for this mechanistic stuff, we can't use the closed source models because you need the weights, right? But I actually think there's maybe there's a silver lining to that, which is we want results. We're mostly interested in results that are somewhat reproducible across things. So one of the most exciting things I was most excited about with this circuit work was the fact that Wang et al. Paper found this circuit on GPT-2 small. We found the same thing on GPT-2 medium, and then we found the same thing on Bloom. And you're like, okay, good. Like this is a real thing, right? And I don't expect it to be exactly reproducible. I'm somewhat less interested if nothing at all like it occurs in the other models, right? We want stuff that's a little stable. I think other sciences deal with this too, right? Like I'm going to collect some humans and do some psycholinguistic study, and someone else is going to collect different humans and do a different one. And if you can't reproduce across different subjects, it doesn't mean there's nothing there, right? But like, I don't know. So maybe it can be embraced a little bit as making sure we focus on the signal and not the noise.
Terrific. Go have some lunch. And now some virtual applause.
Thank you so much.